PLA that will withstand 150 degrees? Seriously? Will it withstand 150 degrees? Or is it going to look like this? I don't know. Stick around. We're going to find out. Hey everyone, welcome back. I'm Scott, Edge of 3D, and so Polymaker's launching a new filament right now. Just dropped. High Temperature PLA. And they've sent me a lot of it. You know, most of my stuff that I do is in black and white. Well, the videos are in color, but the materials I use are black and white for my testing. But they sent me some colors. This is one of them, the High Temp PLA glass fiber. So this is glass fiber filled material, power tool yellow. And this is just the regular High Temp PLA. Gradient Fire is the name on this one. So if you want to see what they look like printed, well, here's a Gradient Fire duck. There's a power tool yellow duck. Nick from Polymaker suggested I print Jeep ducks, so we have Jeep ducks. You can blame these on Nick. Also printed a few other items. Of course, a Flexi Dragon, and this is in the power tool yellow. And a Flexi Dragon in the Gradient Fire. Right here, put a video up right quick. This is a time lapse. This is actually an ANET A8 printing a duck. And just to prove it can be done on an old open frame printer. These dragons were all printed on the Creality K1, which is right there behind me. The ANET's right there. I printed a bunch of this stuff on the ANET. So the claim is that this material is, I got to look over here at the screen so I get it right. It's heat stable to 150 degrees Celsius once the product is annealed, and you have to anneal it at 110 degrees Celsius for 30 minutes. A little toaster oven will do that. I have a big lab oven that I'm fortunate to be able to use to anneal, but a little toaster oven. Throw your part in there. You have to do the conversion to Fahrenheit if you're in the country where we use those units. Anneal it for 30 minutes, and then let's see if it lives up to the claim. But heat stability is the ability of a part to maintain its form and shape with little or no outside force, just its own weight. Heat resistance is the ability for it to maintain its own shape with a load on it. And of course I did loads. Right here's the test. I don't have the weights here, but I have 50-gram weights that I hang on each one of these hooks, or the places there's still hooks left. The PETG, it sadly just dripped its hook right off. The ASA glass fiber pulled the hook out. The 3DX Max ASA did something weird and it shrunk. And of course the PE6 carbon fiber that was heat treated, it never moved. We'll get into all that in a minute. So I tested the heat resistance under load. And we grabbed the picture and put it over here on the other screen, and we'll switch to that right quick. And let me turn on the mouse cursor. Sorry, the lighting inside of the oven isn't all that great, but this is at 110 degrees Celsius. And you can see that, well, the ABS and the ASA, they've failed. The ASA Max has failed. The PETG has way failed. Now this is the heat, or the High Temp PLA glass fiber that's unannealed on this one right here. This is the annealed part. So it's dripped a little bit, but considering that's 50 grams hanging 100 millimeters out on that tiny little part, that's pretty damn good. This is the High Temp PLA, not the glass fiber, again unannealed, and you can see how much it's pulled down. But I want you to notice that neither the High Temp PLA nor the high temp PLA glass fiber that are unannealed have failed near as much as the ABS and the ASAs or the PETG. Now the annealed stuff, it's doing really, really good. So that's, I'll put a time lapse up here right quick and let it play through. I put these in the oven and I take pictures at intervals and I put it into a time lapse, and you can see as it progresses through. But their claim of heat resistance is 110 degrees Celsius. I'm putting a 50-gram load out on the very end of these, and this is the weight. It's 50 grams. The piece itself is 10 grams, and then I add 4 10-gram discs to it. That's 50 grams. Hangs out here on the end of these like that in the oven. That's a lot of weight for a piece that size. And for those to hold up at 110 degrees under that kind of load, I would say yes. Yes, the claim of being heat stable at 150 degrees is absolutely spot on, or heat resistance. So the next one is heat stability, and what heat stability is the ability for something to maintain its shape at a given temperature under its own weight, so it doesn't collapse under its own weight. And I printed a bunch of different samples. I printed some stuff in ABS and ASA and COPE and PC Max, as well as the high temp PLAs. This is the glass fiber. This is the gradient fire. And here we have another, this is just the regular Ht-Pla, and this is the glass fiber PLA. So, let me bring the document up here right quick. So we'll jump over here to the other screen right quick, and I'll show you the methodology that I used on this. The objective is to evaluate the thermal study of high temp PLA, specifically assessing the manufacturer's claimed material that achieves heat stability to 150 when annealed at 110 C for 30 minutes. And I'll leave this up, and I'll also put this on a Google Drive and put a link to it in the video description so you can read through this. This is the objective, my parameters, the rationale, and the real world simulation. And what I wanted to do was simulate. First off, let's talk about the market that this is aimed for. This is not for the people wanting to build boron printers, though. Based on my testing that I've done, I am going to build a V0 out of this stuff, just to see. A lot of people have open frame printers. I doubt very many have ANAD A8s left. I just happened to. Dug it off the shelf, fired it up, and printed a duck. Printed a couple of ducks, actually. But Ender 3s and those the bamboo A1s and that, the open printers. And they want to take the next step, and they want to move up to a boron, be it a 2.4 or, let me scoot over a little bit, that's a boron 0 right there. Just off screen, here's a mercury, also all printed. But the problem they have is they got to print all these parts, and everybody tells them you have to have ABS or ASA. And printing that open air can be done. I've done it. You can put them in a tent, you can put a box over them. But what if you can print it in PLA and you can anneal it in your toaster oven and it works just as good? Or in the case of this right here that you already seen, when it was at 110 degrees, even the unannealed stuff was holding on better. That is not the market this is intended for. But I had to go there anyway. The market that this is intended for is the people that print trinkets at home on their open printer. And then kids take their toys, they head off to Grandma and Grandpa's for Memorial Day weekend. It's South Texas, the sun's out, it's hot. They leave their toys laying on the dash or somewhere else in the car, or people print dragsters and they leave them in hot cars in Indiana. And they come back to this. So the idea is a material that can be printed with just a regular printer, annealed for a short amount of time. 30 minutes is nothing at 110 degrees, and it'll withstand shipping in a hot UPS truck for the guys and gals who run small print farms. You know, they're printing little trinkets, shipping cross country. They sit in a hot UPS truck all day. The customer gets their box and they're expecting something like this, and it comes out of the box like this, and they're not happy, and the people are losing money. Well, no more. I tested it all the way to 150 degrees. I started at ambient. I printed out all these different samples. I devised a test, which I lost the fit pins, but a thermal stress test artifact, which it's got a flat wall here with a base here, and the idea is to see if it stays at 90 degrees. The box right here is 20 by 20 millimeter, and the idea behind that was to see, you know, at temperature, does it maintain, or actually 25 by 25, and it's 24.99, 24.97. We'll get to those in a minute. And then the unsupported arm sticking out here, does that stay parallel to this under its own weight? Started at ambient temperature. Every 20 minutes I raised the temperature 5 degrees. I took a picture in the oven. When it started to hit about 80 degrees, I started to pull the trays out with all the different things on them and take a look at them and see what was failing. And let's go through that. So first off, let me cut way too much stuff here on the desk. And now where did I set my mouse? It looks like a duck. Don't know what I just did here, but we're going to drop that off here, minimize this, and we're going to start over here with the 80 degrees where I started to see failures. So let me transfer over that screen. So in order here, this front one is PC Max, Polymaker PC Max. The next one is Polymaker Silk PLA. The third one is Polyterra PLA, and the last one is the High Temp PLA. The High Temp PLA was annealed 110 degrees, 30 minutes. And at 80 degrees, the silk was starting to fail. The Polyterra was sagging a little bit. The PC Max was actually, it was going up. And then we have the duck at 80 degrees. And it doesn't really show in this picture, but this one right here, which was COPE, not to be confused with COPA, but the new COPE Panchroma, it was starting to have a little bit of deformation I could see in it. At 100 degrees, well, we just lost 100 degrees on the artifact, so we'll bring the ducks over because I clicked the wrong button. You can see on the ducks, the poor COPE, it's headed south. The one farthest one in this middle row is the PC Max. It's starting to show a little deformation, but it's not there. 110 degrees on the artifacts. Not much has changed. The COPE is now sagging. The PC Max is now sagging. The Silk PLA is already dropped all the way down, and the wall's starting to tip over. The Polyterra is starting to sag, but everything else holding on. The High Temp PLA holding on perfect. So I let it set for 2 hours at 110 degrees to see if anything changed. And really no change. It looks pretty much the same. Then I cranked it up to 150 degrees for the last hour and a half. And we have lots of stuff that went wrong here. Poor little COPE is gone. PC Max down here, he's got his tail sticking up. The rest of them's gone. And plain old ASA, ASA fell asleep. His head's tipped over. Nothing else on the plate is harmed, and we'll go to that in a minute. And finally, the artifacts at 150 degrees. This is PC Max, and it did some strange stuff. We're going to look at it up close here in a minute. Silk PLA, really, it started to sag over on the wall. You can see that. But other than that, not anything real bad. The Polyterra PLA held on surprisingly well, other than the arms sinking down, and the walls started to come just a little bit off of 90 degrees. And the High Temp PLA is being blocked by my thumb, but you got to remember that tray right there is 150 degrees Celsius, and those are just lightweight cotton gloves, so I couldn't really hold it too well. But we'll look at these up close right now. So there you go. Does it hold up under its own weight? These right here, these are all High Temp PLA. They were all in there at 150 degrees. Absolutely no deformation anywhere in the model whatsoever. They held on perfectly. So, yes, this is ASA. ASA, well, he's sleepy. He's a little tired. COPE, he's face down in his drink. He's down for the count. PC Max, I'm really not sure where the duck even went, but we still have a tail. But the duck and the Jeep are gone. Here's a couple of surprising ones. PLA Silk. That was in the same oven as all three of these that are melted. This is PLA Silk. Good look at that. The grill's all still perfect. The model's still perfect. Polyterra PLA. The grill's still perfect. The model's still perfect. These were in the same oven. They were on that same sheet. All of these ducks were on the same sheet. So, another one is a dual color Polyterra, black and white. I don't remember what the exact name of it is. I printed it. It's a Flexi Dragon. Same as these Flexi Dragons. It was on the sheet with these Flexi Dragons at the bottom of the oven, up to 150 degrees Celsius, and it's PLA. It held on just fine. So I'm going to do a lot more temperature testing on PLA. I want to get to the bottom of this. But we had some PLAs that were surprising. Silk and Polyterra PLA. This is just regular PLA. There's nothing. Everything's perfect on this dragon. These dragons were heat treated. Okay, this dragon was not. Take a look at that. These ducks were not heat treated. PLA Silk, Polyterra PLA, 150 degrees Celsius. So now let's look at the artifacts tests. And let's look at the PC Max first. I only did 4 of these. I should have done a whole bunch more, but I only did 4. And so I'm going to use the High Temp PLA as the model because this is what it's supposed to look like and what it did look like when it was first printed. This is PC Max after being in there at 150 degrees. It grew. As you can see, it grew. It shrunk. It fell over like a bad night at a cheap bar in Tijuana. DC Max doesn't hold up to temperature. Polymaker PLA. Again, this box is supposed to be 25 by 25. Let's see how much it deformed. 24.43, 24.37. So there was some shrinkage here, but not like you'd expect from a PLA. And you know, the arm shrunk a little bit, but it didn't come all the way down. The back is a little bit out of kilter. It's not a 90-degree angle anymore. Silk PLA, it tipped a little bit more. This came all the way down till it's touching. The box on it wound up at 24.3, so it had a little bit more shrinkage than the Polymaker in 24.25. And finally, the heat-treated PLA. Now, if you really look at this close, and I go get a engineer's right angle, there is some curvature to this back now. But it was in there at 150 degrees. This is still parallel to this right here. So, all things considered, it held up pretty dang good. And as far as shrinkage goes, 24.94, 24.98. So negligible shrinkage on the parts. As far as the material goes, pricing on it, you pull that back up here right quick. It's all available today in US, Canada, and the EU. Other countries will be coming along shortly, but the regular colors of the High Temp PLA, which would be your blacks, whites, that sort of stuff, this here, these are going to be $24.99 a roll. The gradient colors, which this is a High Temp PLA gradient, this is going to be $29.99. And then the High Temp PLA glass filled are going to be $29.99. So all available today. I'm going to do a lot more testing on this. I ran it through my normal battery of tests. We can take a look at that right quick. Here we have, let's see, PLA. And these are x-axis where it yields at, where it breaks at. It didn't make a lot of difference in the regular High Temp PLA between annealed and regular as far as the x-axis, but it lost quite a bit on the glass fiber, and the glass fiber came out higher, and I'm going to show you here when we get over and look at the IZOD. It's interesting. As far as how far it stretched before it breaks, well, the High Temp PLA glass fiber unannealed stretched a lot further than the others, but it held on more. And then the break points, they coincide right along with the stretch points or the yield points. Layer adhesion, nothing really good, nothing really bad, but layer adhesion did go down on both of them when annealed. Now I only did 5 samples of each, so I haven't done extensive testing, but these were all printed on the same exact printer. They're printed at 220 degrees on the hot end, 60 degrees on the bed, and layer adhesion, I mean, it was acceptable before it was annealed. After it was annealed, it dropped down some. Still an acceptable number. Direct thread, High Temp PLA glass fiber, unannealed, held on best, and on both of them. Once they were annealed, the strength went down. Heat sets, strength dropped off considerably on the annealed parts. I don't have an explanation for that. And finally, the IZOD shock. Typically a filled material, glass fiber, carbon fiber, whatever, is more brittle. So if this black Ht-Pla and this black Ht-Pla glass fiber are the exact same base, with this one just having glass fiber added to it, then the glass fiber is adding strength. That's all I can say. It's showing right there, 29.4, 28. Shows it over here too, 174, 204. But the Izod shock, this should be the opposite. These should be higher, these should be lower. No, I didn't get the parts mixed up. And all this is available. I'll put a link to this page, and you can go over here into the comparison. Let's just take let's take a high temp PLA and a high temp PLA glass fiber, and let's go down here and compare them to it's an ASA glass fiber. So there's your ASA glass fiber, x-axis yield. Your high temp PLA glass fiber, x-axis yield. Do I need to say more on that one? This is just how far they stretched before they yielded. Breaking point. Layer adhesion. Well, PLA beat ASA glass fiber on layer adhesion. Both ways. Direct thread. High temp PLA glass fiber. Heat set. The high temp PLAs beat the ASA glass fiber. Izod shock. Well, one under, one over, all right in the same range. I don't know what to tell you. Yes, their claims are absolutely validated as far as I'm concerned. You can print this. It's safe to 110 degrees, 100 degrees, 90 degrees. I would say I'm going to build another one of these, a Voron V0, using this material. In fact, I might do it in Power Tool yellow with some gradient fire highlights or something. I'm going to try it, print with it, see what happens. Again, pricing on it, not out of range, especially for the kind of performance. $24.99 for regular colors on the high temp PLA. $29.99 for the gradient colors, like this gradient fire, which let me grab this here. This is a spool of the gradient fire right here. I don't know how all the camera's going to pick up the colors on it. It kind of goes from a red to an orange. And then the $29.99 for the glass fiber right there. Power Tool yellow. So there we go. I say the claims are validated. Affiliate link in the video description down below. It's live now. Appreciate it if you use my affiliate link to purchase this. Gives me a little kickback to the channel, helps pay for some of my expenses. And if you like this content, give me a thumbs up. If you want to see more of it, hit the subscribe button and hit that bell icon. You'll know when I drop the next video. As always, I can't thank each and every one of you enough for sticking around and watching these videos all the way to the end and supporting my channel. And as always, peace out. We'll see you on the next one.